Yeah, hi everyone. It's my pleasure to introduce Carlo Beenakker as the speaker of today's JQI seminar. So just briefly, I mean, Carlo graduated from Leiden University in 1982, getting his and got his PhD in 1984. He was at well, after some postdocs, he was at the Phillips lab from 86 to 96, and then he moved. Well, but part of that was as a consultant. He moved to back to Leiden basically in 91. So Carlo, I've known Carlo for as long as I've been working since I stopped doing band structure and doing condensed matter, like Majorana stuff and etc. So for a while, and so Carlo's kind of a fixture in mesoscopic physics. That's the way I view him. I mean, so some of his earlier papers, I guess, back from his Philip days, on quantum point contacts, Josephson junctions, and Coulomb blockade are like where I go back even now to clarify things. And Carlo has won a number of awards. He's a fellow of the American Physical Society. He won the Spinoza Prize, and I guess he was knighted in the Order of the Dutch Lion in 2015. It would have been, I guess, as we were discussing, it would have been we're really getting half the Carlo experience by not having him here. If you search Carlo Beenakker's CV, which I just did, and that's and the first, like, his page is very entertaining read. So I recommend it. It connects him back to Bernoulli, etc. So, and there's the flute concert too. All right, so I won't deprive you of Carlo anymore. So Carlo, please take it ahead.
Very good, thank you. It's fun to be here. It would have been way more fun to actually be there physically, but this is what we'll have to do now. So I'm going to share the screen now. Let me see if that works. And I will start. Let's see. I think yes, I think you guys see the presentation. You see my cursor, you see me.
Yes, it's fine.
So I think it should just work. And so I like to do this, like we do usual talks. So I would encourage you to interrupt me if you have questions, right? So because I don't have the experience of looking into an audience, and so it's just me talking to my computer. And to keep me awake and interested and engaged, it really helps if you guys interrupt me, stop me. And don't worry that we'll run over time, because the thing which I'm going to tell you is really kind of simple, and so we'll get to the end in due time, even if there's lots of interruptions. So by all means, stop me for questions. So this is very, very recent work. Actually, it's the first time I've talked about this. So I made this presentation especially for you, and it's a project we put on the archive just 2 weeks ago, and I think my 4 co-authors have all joined the Zoom thing, so they're here. That's Michał Prochowski, Gal Lemut, Omri Ovdat, and Inan Chadagideli. And yes, it's about Majoranas, it's about Landau levels, superconductivity. It's a bit of a new twist to pretty much an old story now, but I think it's an interesting new twist, and it also has some nice images. Here's one image, and I'll walk.
I'd like to comment. This is Charles. I'd like to comment on that image. Several of us will note that it looks like the fork diffraction grating that's used to create an orbital optical angular momentum vortex state.
Yeah, there are vortices. There are absolutely vortices here. I don't think there's an optics angle, but there are vortices. There's a bifurcation point, and we'll get to this thing in a moment. But actually, this whole project started not so long ago. It started in last fall, just last October. I contribute once a year to Journal Club of Condensed Matter. Some of you may know that it's a blog, and this goes like this: that Chandra Varma emails you and says, "It's been a year. You have not written anything for the Journal Club. Please send me something before the end of the month." So I panic I say, oh my goodness, I don't want to disappoint Chandra. What should I talk about? And fortunately, there was an experiment which had just appeared on the archive in October, which I found kind of intriguing. And I wrote to Chandra, I will write a commentary on that experiment. And writing this commentary, going into that experiment somehow motivated this investigation, which I will tell you now. So there's an actual experiment underlying this, and the experiment is by, it's a big group from Beijing, but one name which you may recognize is Liang Fu, next to last author from MIT, who's, with Charlie Kane, basically the father of the whole field of Majoranas and superconductors. And this is an experiment, I would say the first really convincing and conclusive observation of a Bogoliubov Fermi surface. So Bogoliubov particles, Bogoliubov quasiparticles are the quasiparticles in a superconductor. Superconductor is gapped, but there may be situations where you can have subgap excitations, and these subgap excitations are coherent mixtures of electrons and holes, and the name we give them is Bogoliubov quasiparticle. They don't usually have a Fermi surface, but it is possible to actually make a Fermi surface for Bogoliubov quasiparticles. And the mechanism, at least one mechanism by which this can be done is the mechanism which is shown here. This is sometimes called the Volovik effect. This is a picture which I copied from Volovik's article from 2006. So the idea is this. So here you see this RS is the rho S is the superfluid density, number of Cooper pairs. And then you apply a supercurrent. You apply a supercurrent, so a supercurrent velocity. You apply a supercurrent to a superconductor. And first, nothing happens. I mean, the superconductor will just carry the supercurrent as if nothing happened. It's fully gapped. And then you might think that, okay, if the supercurrent becomes too big, then you exceed the critical current and the superconductor dies. The gap closes, which is true. Then the number of Cooper pairs goes to 0. But if you're lucky, there will be an intermediate regime where the density of Cooper pairs starts to decay, but it's not directly 0. And in this intermediate regime, you will have a superconductor which is not fully gapped, but it's still superconducting, and it will have a Fermi surface. And this Fermi surface will be very unusual. That was what Volovik discovered. It will have segments which are mostly electron-like, and it will have segments which are mostly hole-like, and there's a transition from electrons to holes here. And this is what Liang Fu calls a segmented Fermi surface. So it's a Fermi surface which is composed of electron and hole segments joined together. And the math for this is really very simple. The math is this, that if in perturbation theory, if the supercurrent velocity or supercurrent momentum is kind of small, then the correction to the energy spectrum is given by taking the bare energy spectrum, the bare dispersion relation, and taking the derivative and multiplying by PS. So that's first order perturbation theory. And obviously, if this delta EP becomes bigger than the gap delta, then you will have states at the Fermi surface. And that's sometimes called, this correction is sometimes called a Doppler shift. It's what happens if, it's an energy change which happens if you're in a moving frame. And the moving frame here is the superflow, the supercurrent momentum, the superflow. Now, in a conventional superconductor, all of this actually I think goes back to Landau, who noticed that this gave an upper limit to the superflow which a superfluid might be able to carry. But in a conventional superconductor, if you actually look at this condition here, right, PS exceeding delta over VF. Now, delta over VF is h bar over the coherence length, right? The coherence length is h bar VF over delta. So typically when the supercurrent momentum exceeds the coherence length, that means that the current has exceeded the critical current. So if you just try and do this in a conventional superconductor, this interval here is not there. V star will be equal to Vc, everything is killed immediately. So the trick which these experimentalists used to be able to have a window of opportunity, the trick which they used is a trick which is very familiar to us now. It's a trick where you don't work with bulk superconductivity, but you induce the superconductivity by the proximity effect. So you have some big bulk superconductor, very strong superconductor, huge gap, and then you put on top some material which in this case it's a topological insulator, in which you induce a much smaller gap, you induce a much smaller gap. And so you can have a large supercurrent flowing through the bulk with a big PS, and still this PS will be bigger than the induced gap, but it will be smaller than the bulk gap. And so then you have a situation where on the one hand, your PS is bigger than the induced gap, so you can close the Fermi surface in bismuth telluride, but it's smaller than the bulk gap, so superconductivity will still exist. And the way you induce, there are many ways in which you can induce the superflow. The way these experimentalists did it, they just applied a parallel magnetic field. Parallel magnetic field creates screening currents, and these screening currents mean that there will be a superflow perpendicular to the perpendicular magnetic field. Excuse me, perpendicular to the parallel magnetic field. You have an in-plane magnetic field and a superflow perpendicular to that. So this is the setup, and it works. It works brilliantly. And they saw this by really imaging the Fermi surface. The way you image the Fermi surface in these materials is you take a scanning probe. With the scanning probe, you make maps of the density of states. In real space, you make maps of the density of states in real space. You Fourier transfer of the maps, which you go to momentum space, and then you image the Fermi surface. And here's what they saw. So the left one is where they just take this material as it is, no magnetic fields, and they see nothing. Basically, their image is blank because there are no states at the Fermi surface. There are no states in the gap. Now, if they do not apply the magnetic field, but they have a large bias, then they go above the gap, and then they see just the bare Fermi surface of bismuth to telluride. And the Fermi surface of bismuth to telluride is a hexagon. So it's not a circle, it's a hexagon. And so you see the hexagon here. This is the hexagonal Fermi surface of just bare bismuth to telluride. Now they go to 0 voltage. So they are in the middle of the gap and they apply a magnetic field. And then what you see is, so the magnetic field is in this direction. So the superflow is in the perpendicular direction, it's here. And indeed, they see the gap closing in the directions perpendicular to the magnetic field. So here the gap is still present. Here the gap is still present, but here you see the hexagons appear. And so this is a real cool, really kind of unambiguous, beautiful demonstration of a Bogoliubov Fermi surface. As an aside, much of, let's say, experimental papers in this field tell a story. I'm quoting now an observation by Anton Akhmerov, who noticed that the way much of experimental physics in this field has progressed is it's by way of storytelling. There are other fields where it's very different. High energy physics is very different. High energy physics doesn't tell a story. It shows you a peak, and then it does data analysis at 5 sigma, whatever, and tells you this is what we observed with this level of confidence. But in condensed matter, experiments are so difficult and interpretation is so ambiguous that papers tell a story. They try to bring you along a certain path to convince you that what they've seen is really what's happening. I'm pretty sensitive to this because, as you may know, you may or may not know, but Dutch newspapers have all exploded in the last 2 or 3 days because of the Majorana story, which no longer seems to be what it was. The observation of Majorana fermions no longer seems to be what it was. So that's a story which somehow has a different twist. So here, this experiment tells a story, but I think it's a story which is easy to follow. It's very difficult to somehow say, no, they're really seeing something else. In particular, because of this anisotropy here, that they see the Fermi surface close in one direction, not in the other direction. I think this is really a demonstration that the simple effect of the simple Volovik effect is really there. So this is the please.
Carlo?
Yes,
Jay. So quickly, I mean, again, this is great. I actually I hadn't followed this at all. Or I missed this completely somehow, I should say better, which is sad. But so to see this Fermi surface in STM, you need the story of quantum interference and disorder, right?
Yes, exactly.
So
no, they're scattering from impurities.
Right.
And
is that does that add wrinkles to when you interplay with the magnetic field, which would have some additional effects on suppressing gaps?
Yes, I mean, the analysis here is just kind of straightforward, and it's not more sophisticated than this. And yes, you want to do quantum interference, so you need some impurity to set up wrinkles to see the Friedel oscillations. You want to see the Friedel oscillations. This would be very simple. Let's say if it would be a circular Fermi surface, then you would see just then you would see that you have these Bessel functions oscillations. Fourier transform would give you one dominant k vector. There's one twist actually, which is, and this was fully incorporated here in the analysis. The STM only sees the electron component of the density of states. Only sees the electron component. And so you have to be careful in your interpretation that you're imaging only the electron component of the density of states, and you can somehow see it here because remember I made this is like a smiley, right? It's a lozenge type of shape, but here they see only half of it. So the fact that they only see this thing and not the closed thing is because they only see the electron part of the Fermi surface. So, if you look at the paper, actually, they have another set of 3 plots which show the numerical data, and it looks kind of similar. So I'm sure there's more to tell here, and I'm sure it's not the end of the story, but this is basically what motivated me. Now, what motivated me is actually seeing this and asking myself, okay, if we have a Fermi surface, could we see a Landau level? What do you do if you have a Fermi surface? You apply perpendicular magnetic field. There's no perpendicular magnetic field. There's just this parallel magnetic field which just drives the supercurrent. You apply perpendicular magnetic field, you should see a Landau level. You should see a superconducting Landau level. Which, if you think of it, seems like a contradiction, right? How can you have a superconducting Landau level? I mean, superconductors don't like, first of all, quasi-particles in a superconductor are like charge neutral. What does it even mean to have a Landau level? And so this basically was the question which I asked my students basically. Can we be motivated from this experiment and say, apply a perpendicular magnetic field and then you'll see a superconducting Landau level. Now, to somehow prepare you for this, I'm going to go back in time 3 decades. So there will be a little bit of digression now, because if you Google superconducting Landau level, you come back to something which goes back way before topological insulators, and this is the story of high TC. When high TC was discovered in the 1980s, these 3 giants, actually, and after it was discovered that high TC is D wave, and that D wave has nodal fermions, point fermions. I might add here, somehow a point fermion is not considered a Bogoliubov Fermi surface. It's a bit of nomenclature, but somehow we like to call Fermi surfaces if it's extensive. If it's just a point node, the jargon of the field is these are nodal fermions. It's not a Fermi surface. It's a point. But anyway, in a D wave superconductor, you have point nodes. So you have Dirac fermions in the gap, and these 3 giants of the field. So that's Anderson, that's Schrieffer, and that's Gorkov, I think. I think it's Gorkov. Pretty sure it's Gorkov. Came up with the idea: could we have Landau levels in a superconductor? And they wrote a paper on this. And this is actually from Phil Anderson's paper. And they noticed actually that because it's Dirac fermions, the Landau levels will be relativistic. So they realized that the Landau levels would go like square root of n, not like n, and that there would be no n plus 1/2. So we would have this anomalous Berry phase cancellation of the 1/2 from Schrödinger equation, and that you would have this anomalous, what's now called the anomalous quantum Hall effect. 1998. Now, this paper by Phil Anderson is on the archive, and it was never published. It was never published for a reason, because I want to, this is just my own small comment. I'm pretty sure if this would have been published and would have been part of the, accepted literature, then there would have been no Nobel Prize for graphene. Why not? Because the Nobel Prize for graphene really came because of the Landau quantum Hall effect. It came because of the relativistic quantum Hall effect. And if you would have seen this in superconductors 2 decades earlier, it would have been just a new manifestation of Dirac fermions. But we know all about Dirac fermions. No, the reason that all of this somehow died is because it was wrong. It was completely and totally wrong, beyond any rescue. And the paper did not appear, and the reason it was discovered pretty early that it was wrong, and this was basically the work of Marcel Franz and Zlatko Tasanovic, who realized that no, if you take a superconductor, it's called unconventional because it's D-wave. It's not topological. It's unconventional, and in fact, if you have a magnetic field in a D-wave superconductor, you see Bloch waves and not Landau levels. So just extended waves, no Landau level quantization. And the reason is that, of course, the magnetic field will not penetrate. Well, it will create a vortex lattice in a superconductor. By the way, Anderson and Schrieffer were very well aware of that. I mean, this is not something they overlooked. They were very well aware that the way a magnetic field penetrates a D-wave superconductor is by vortex lattice. But it's a strong type 2 superconductor, and strong type 2 superconductor means that even though the magnetic field penetrates in the form of a vortex lattice, the magnetic field is very nearly completely uniform. So we have to take this into account. It's not some point magnetic field. The magnetic field has just tiny wrinkles. It's a completely uniform magnetic field. So from the classical point of view, you'd say these quasi-particles will just feel a uniform magnetic field. However, the vortices, it's more than a magnetic field. It's also a phase which winds. And so there will be scattering. These quasi-particles will be scattered by the phase which winds around the vortices, quantum mechanical effect. And I think it was Melnikov who first realized this, that this quantum mechanical effect will be a strong scatterer. So quasi-particles in a D-wave superconductor are strongly scattered by the vortices, even though the magnetic field is uniform. They're strongly scattered by the vortices. And what Franz and Tasanovic discovered is that this strong scattering completely kills the Landau levels. So these red peaks, this is the zeroth Landau level. The red peaks is what you would guess if you said, forget about vortex scattering, right? Then you would have a peak in the density of states, one peak at 0, and a peak at 1/2, a peak at 1, a peak at square root of 2, a peak at square root of 3. So you would have these peaks in density of states. And Franz and Tasanovic, this is a computer simulation, they found that there's no peak at all. In fact, there's a dip. You see here the dip, that's the conical singularity. It's the Dirac point, the Dirac spectrum, which you would expect.
Carlo?
Yes, please.
This is Bill Phillips. It seems to me that yes, this vortex lattice would scatter things, but I would have thought that since it's a lattice, that it would be Bragg scattering. And so I'm wondering whether that comes into.
Well, it is. That's why it's Bloch waves. No, it's Bragg scattering. Of course, it's a period. You go to the magnetic Brillouin zone. You go in the magnetic Brillouin zone. You have Bloch waves. That's why the title says Bloch waves. They're not Landau levels. They're Bloch waves.
Okay, fine. Yeah.
Absolutely, they're Bloch waves. They're Bloch waves, but not Landau levels.
Yeah.
So they just disperse. And in fact, it was a later paper by Marinelli, Halpern, and Simon actually showed rigorously that the Dirac point is preserved. So what happens because of the vortex scattering is that the Fermi velocity is renormalized. So this slope here is different, but there's no Landau level. So that was the end of this story. And 2 years ago, in some work which I did also with Michał Pachowski and Inan Chadagideli, we showed actually that the Weil superconductor, so it's not Majorana, but it's somehow something which triggered us then, that in a Weil superconductor, which also has Dirac fermions, it's point nodes in the spectrum. In a Weil superconductor, actually, so in zero magnetic field, here I show you, hang on. So here I showed you density of states. Density of states is a function of energy. Now I'm going to show you the same thing, but not density of states, but band structure. So I'm going to show you energy versus momentum in the magnetic Brillouin zone. So here in the left panel, you see D-wave superconductor, energy versus momentum. The dashed lines are in zero magnetic field. You see the Dirac cones here. And now you see what I said. I said just a moment ago that a vortex lattice will renormalize the Fermi velocity. That's what you see here. You see here that this slope is changed. And if you really, if you're a lover, you have a lover's eye, you'll see this is the Landau level, this band. This band is the Landau level. And here's the next Landau level. So there is something like a Landau level, but it's completely distorted and broadened. And in particular, at the Dirac point, you see a zero density of states. So this is D-wave superconductor. Now you take Weil superconductor. Weil superconductor, if you don't know what Weil superconductor is, it's just graphene in 3 dimensions. I need a third dimension here, right? I need a third dimension here. So it's graphene in 3 dimensions. And so here we have a Dirac cone, very much like in a D-wave superconductor. But now I apply magnetic fields, and you see, bomb, I see the same Landau level, but it's flat. And even the 2nd and 3rd and 4th Landau level, there's some dispersion, but some broadening, but not much. So you might ask, what's the difference? Why is a Weil superconductor different from a D-wave superconductor? And the difference is chiral symmetry. So chiral symmetry, I'll tell you a bit more somehow mathematically what chiral symmetry is. It basically says that the Hamiltonian anti-commutes with some operator, some unitary operator. There's some unitary operator in the Hamiltonian anti-commutes with it. And this chiral symmetry, which is present for Weil fermions. So Weil fermions have a certain chirality. One way to think of chirality, that's typically how it's explained, is if chirality means that there's a sort of spin degree of freedom. If the particle moves in this direction, the spin rotates clockwise. If it moves in the opposite direction, the spin rotates counterclockwise. So that's a way to somehow explain chirality. And Weil fermions, they're like neutrinos, and they have a certain chirality. They can be left-handed or right-handed. Nothing like this in a D-wave superconductor. There's no notion of chirality in a D-wave superconductor. And it's the chirality which protects the 0th Landau level. I'll give you some of the theory background for that in just a moment. But that's what's happening here. So this is some of the prehistory. This is older work, but this somehow primed us for this and said, oh my goodness, there should be something really fun here if we're going to play the same game not with Weil fermions, but with Majorana fermions. And obviously Majorana fermions are way more cool than Weil fermions. Okay, back to the topological superconductor. So here it said unconventional superconductor. Now we go to topological superconductor. So this structure here. So take a conventional S-wave superconductor, put a topological insulators, bismuth to telluride on top, apply a magnetic field, perpendicular magnetic field. That goes back to Fu-Kane. So we actually call this now a Fu-Kane heterostructure, Fu-Kane superconductor. A Fu-Kane superconductor is a proximity-induced superconductor where the material in which you're inducing the proximity effect is a topological insulator. And what Fu-Kane discovered is that if you do this, so forget it for a moment about the superflow. The superflow is this new edition that's also Liang Fu, but that's 2020 edition. So forget about the superflow. You just have the vortices, vortex array. And what Fu-Kane discovered is that each vortex binds a Majorana zero mode. What does it mean? It means that there will be a state that's zero energy. Zero energy means in the middle of the gap, so there's the gap. So zero energy is a very specific energy. It's not relative to some other energy. It's in the middle of the gap. There will be a state in the middle of the gap which will bind to one particle, and this particle is a Majorana fermion. And this is now called the Majorana zero mode. And there's braiding and topological quantum computing, and somehow this is I guess this paper has been cited perhaps 10,000 times, and there's certainly 1,000 follow-up theory papers. And it's an obsession. You can rightly say this is an obsession. And there's now quite some experimental evidence for this, that indeed these vortices bind the zero mode. There's some experimental evidence for that, and I'm not going to show that to you because I'm a theorist and I just believe them on their word. And now here I'm showing you, this is a computer simulation. So here you see the vortices. So this is just density of states. Density of states at zero energy. So blue means, dark blue means there's no density of states. And here you see a bright spot. The bright spot is this vortex. But now I've applied a superflow. So now I'm applying a superflow. And now you see the superflow acts like a wind. It's as if there's a wind blowing in this direction, which blows the density in this particular direction. The wind, it has a name. It's not the Lorentz force, because it will be the Lorentz force, but the Majorana fermions are charge neutral, so Lorentz force doesn't do anything. It's called the Magnus force. It's something which is somehow familiar from superconductivity. It's called the Magnus force. And the Magnus force pushes the Majorana zero modes in one direction. And now you might ask, okay, in which direction does it push them? And this is determined by the chirality of the Majorana zero modes. Majorana fermions are chiral. They have a certain chirality. And their chirality tells you if they're pushed to the right or they're pushed to the left. And I can show you that in a computer simulation, because now I change the chirality and you see they're pushed to the right or to the left. I think this is kind of cool. I think this is kind of cool because the chirality of a hang on, this is not what I wanted. The chirality of my fermion is not something which is easily measured. It doesn't leave an easily observable trace. And here I have an easily observable trace. Just apply a superflow, do some whatever STM spectroscopy to image the density of states, and the direction in which they are pushed, it tells you whether they're left chiral or right chiral. So that's, let's say, the first kind of little discovery here. But we want more. We want to, this is not a Landau level. The reason why I don't call it the Landau level is because it's confined. The whole point of a Landau level is that the wave functions are extended. They're not confined. This is a confined zero mode. And so I need to push them harder so that they will escape, right? I mean, the Majorana zero modes are bound to this vortex, but perhaps if the wind becomes really strong, they will escape. And yes, that's what happens. Here you see, in this computer simulation, I increase the wind, I increase the Magnus force by increasing the superflow, and they escape. And as they escape, you can still see a trace of the vortices. The vortices are the bifurcation points. You see the bifurcation point? There's one here, there's one here, there's one here. And actually the direction in which they're pushed, from the bifurcation point, you move to the left here. That's what fixes the chirality. But more dramatic here is the striped phase. So there are these oscillations in the density of states, these stripes, these oscillations in the density of states with a certain wave number. And this is a Landau level. It's deconfined. The density of states is not uniform. I have this vortex lattice. It's not a uniform density of states, but it's deconfined. And yes, Gal Lemot just entered the room. Gal, this is the image which Gal actually admitted to our university's image contest. We had an image contest very recently. He didn't win. He got, I think, second or third prize, but I think it was a cool image. And it's certainly one of the coolest images which has come out of my group in the last couple of years.
Carlo?
Yes.
So is this happening at VC or at V star?
No, this is happening at VC.
Okay.
V star is something which happens when the bulk superconductor dies, and I'm just pushing that very far away.
Okay, so this whole thing would just disappear. This whole pattern would disappear.
If your supercurrent becomes bigger, if your supercurrent becomes bigger than the critical current of the bulk superconductor, then it's the end of the story.
Yeah. Okay.
So I'm assuming here that the gap induced in the topological superconductor is kind of small, and so I can really drive a pretty large superflow so that the bulk superconductor will still remain operative.
Now, what breaks the symmetry that tells us where these stripes are?
Yeah, so that's okay, so hang on. So first of all, there's different types of symmetry. First of all, you see here that at this bifurcation point, things move to the left. Now that particular symmetry, that is the chirality. That's the same symmetry you saw here, you see? Whether, excuse me, I'm not too smart with this. Okay, so whether I move to the right or I move to the left, that's the chirality. That's something which is inherent in the system. I can tell you more about that. I will in just a moment. Now, apart from that, the fact that the stripes are parallel to this, they're perpendicular to the superflow. So if the superflow, if I would rotate the superflow, then these stripes would rotate with it. And what gives the periodicity of this, that's something which a theory will have to uncover, and I'm going to show you that in just a moment now. So now I'm going to shift gears another time. So now I'll have a blackboard with formulas. Not too many formulas, but I have a couple of formulas because some of you may actually say, okay, computer simulations, that's good, but please give us some equations, right? So give me some equations. The first equation will have to be the Hamiltonian, right? What else could I do? So let me write down the Hamiltonian. So here's the Hamiltonian. Let's walk you. I'm going to walk you through it. So it's the thing which is called Bogoliubov Fermi Hamiltonian, which means there's an electron block that's here. There's a hole block that's here. There's something which couples electrons and holes. That's the pair potential. And there's another thing which couples electrons and holes. That's also the pair potential. The pair potential has an amplitude delta 0 and a phase phi. This phase phi will wind around the vortices. Now, if I look at the electron block, it has a momentum. It's k dot sigma, sigma spin. These are spinful particles, so it's like in graphene we would have well, the graphene is probably not the right. In a topological insulator we would have k dot sigma, and we have k dot sigma here as well. So this is like a very strong spin-orbit coupling, momentum coupled to spin. There's a vector potential because of this magnetic field. There's a vector potential minus E in the electron block plus E in the hole block, and then there's the superflow. So the superflow is like a big. You could basically say it's like a gauge field. This is I think this is familiar because if you know about the London equation says that in a superconductor, the supercurrent is proportional to the vector potential. That's the London equation. And so if you apply if you apply a superflow to a superconductor, you're basically imposing a vector potential. And you see the vector potential appears like A dot sigma. In this case, the superflow is in the x direction, so I have K sigma x. And here I have also K sigma x. Okay, so that's so my way of saying this is K is the Cooper pair momentum. It's the superflow, the Cooper pair momentum. So it's the superflow momentum per particle. Phi winds by 2 pound around the vortices. Now there are some approximations or level already made in this Hamiltonian. I'm going to ignore the inhomogeneity of the magnetic field. I'm going to say, this is a very strong type 2 superconductor. So the magnetic field is just completely uniform. I'm also going to ignore, not necessarily, but it's kind of convenient to also ignore inhomogeneities in the amplitude of delta. I will just say, the amplitude of delta, yes, at the vortex core, it goes to 0. I know that. But the vortex core is tiny. This is a strong type 2 superconductor. The vortex core is like a point singularity. So it's completely okay to take delta 0 completely uniform. And we can check that in a computer simulation, but it simplifies life a lot. So this is the Hamiltonian. That's it. And okay, now just a moment. If K would be 0, so if this term would not be there, then this is a very, very, very familiar Hamiltonian. I think first solved by Jakub and Rossi, 1981, which is a classic paper of the field. It's actually the first paper which found Majorana zero modes in a vortex. It was just not in the connection with topological insulators. So basically what Fu-Kane did, it's not they invented a new problem, but they realized that the Jakub-Rossi problem, which was formulated in the context of particle physics, that it had a condensed matter realization in a topological insulator, which is, no small feat. Anyway, for K is 0, the spectrum of this Hamiltonian was solved by Jakub and Rossi. So our task is to remove K, and K can be removed. And this is something really neat here. I learned this from Inan Charagidali. The games you play here are non-unitary gauge transformations, sometimes called chiral transformations. So the first time Inan wrote down this transformation, I said, Inan, there's a small typo here, right? Here you want minus ky, right? It's not a unitary transformation. And then Inan told me, no, the no minus sign here, it's not a unitary transformation, it's a chiral transformation. So the same exponent on the left and on the right. Lambda is this matrix. Lambda is the chirality operator. So before I said Majorana zero modes have a definite chirality, that means Majorana zero modes are eigenstates of the lambda operator with eigenvalue plus or minus 1. Now this lambda operator has 4 elements because this Hamiltonian here has 4 elements. It's a 4x4 matrix. There are 2 components of the spin, and there are 2 components of electron and hole. So it's electron, hole, spin up, spin down. That's 4 components. And this operator here acts on these 4 components. It's called the chirality operator. And Majorana zero modes are eigenstates of lambda. Now, it's a very small exercise that if you do this non-unitary transformation to this H, then you can remove K. That's cool. So unitary gauge transformations can remove A, and non-unitary gauge transformations can remove K. Isn't that neat? That's really kind of neat. And you do that, and then you say, okay, then I'm done, right? Jakub and Rossi solved it. I'm done, and indeed, you're almost done. So you do this, you do this thing, and you find this thing here. So this what I write down here is from Jakub and Rossi. That's the wave function from Jakub and Rossi, and the non-unitary gauge transformation gives you this extra phase factor. But it's not just that it's not a phase factor. That's the dramatic thing. It's not a unitary thing. It's not a phase factor at all. And so if you look at this term here, this explodes, this blows up for A to plus or minus infinity. So hopefully this exponent will kill it. Well, yes, this exponent will kill it. This exponent here will be like, this decays exponentially like delta x or delta r. So as long as k is smaller than delta, then it's normalizable. Now, just a little test here. So this is just a computer simulation where we checked, apologies, the computer simulation where we checked the decay of this Majorana zero mode. Along the x direction, there's no effect. Along the plus I direction, where these exponents add, or along the minus I direction, where they subtract. And you see the simple k plus or minus delta beautifully fits the numerics, so it all agrees. But now comes the problem, of course. If you follow this line here, at this point here, the decay rate crosses zero. Decay rate crosses zero means it will explode. It's no longer normalizable. So the Jacques-Rossi solution, regrettably, only works in this confined phase. So it can explain this wind effect. It can explain that this Majorana zero mode is blown to a certain direction, but it cannot explain the escape. Once the Majorana zero mode escapes, then all of this dies and no longer works, which is good. Otherwise, it would have been a very simple paper. And so then we go to the deconfined phase. And well, we go to the deconfined phase. There are just a couple of steps we take first to make the problem a bit more tractable. First of all, we make a unitary transformation. This is a bona fide unitary transformation to a basis of chirality eigenstates. Then you get this Hamiltonian. So this is kind of the first step. And then you notice that this Hamiltonian here has this chiral symmetry. With chiral symmetry, we mean that it's a Hamiltonian which has a zero block diagonal, and non-zero off diagonal blocks. That's called chiral symmetry. Now, if you have a Hamiltonian of this form, now it's a very simple math to see that if you want the zero mode, so you want h psi equals to zero, then there are two ways to get it. Either psi is u0 or psi is 0u, right? Just u0. So in this way, you're able to reduce the dimensionality of your Hamiltonian by a factor of 2. Instead of solving h of psi is 0, you have to solve psi of u is 0. And psi is a 2x2 matrix, no longer 4x4 matrix. So that's good. That's with just a little work, we were able to reduce a 4x4 eigenvalue problem to a 2x2 eigenvalue problem. But there's more. It's not just a reduction. There's something amazing here, because here you can make contact with this beautiful theorem for math, which is called the Atiyah-Singer index theorem, which says that if you have chiral symmetry, the number of solutions of an equation like this, psi u is 0, actually minus the number of solutions of this equation, is called the index of the Hamiltonian, and it's topologically protected. So this immediately explains why the Landau level, this Majorana Landau level, is flat. Without any calculation, you know that it's flat. Why is it flat? Because of chiral symmetry. So the degeneracy of this Landau level, which says how many modes there are, is the index of the Hamiltonian, cannot change. There's no way you can change this. And so indeed, if you look at this is a numerical plot. The green lines are a numerical plot. You see completely flat because the Hamiltonian has this off-diagonal form. So, okay, so far we've been able to go quite some way without any calculations. There's some stuff from Jacques and Rossi, there's some stuff from Atiyah and Singer. We didn't have to do any calculations, and we got quite far. But
Carlo, I should give you the standard 5-minute warning.
No, don't worry. I'm
just doing my job.
People who know me knows I never go over time. So now comes some work, right? Now we have to actually we want to find the striped phase. We want to find the striped phase. How do we find the striped phase? Well, first we do this. We factor out the envelope. So we factor out this ugly exploding envelope from the chiral transformation. We have to get rid of that. If we factor this out and we add another auxiliary field Q, and we make a clever choice for Q, then lo and behold, everything drops out. It's like a miracle, right? Now you have a new 2x2 problem. The phase is gone. The vector potential is gone. This looks like a baby problem, right? Everything's gone. But of course, it's not quite gone. It still enters via the conditions of normalizability and single valuedness. So the problem is now some very unusual problem, a very, very simple differential equation with a very complicated condition that your solution has to be single valued and has to be normalizable with this envelope. So that's a very unusual problem. We can actually simplify this even further. This is 2 by 2. We can go to 1 by 1 if we make this substitution. So util is Fg, G is this form, then F satisfies this Helmholtz equation. And this is really the heroic work of Michał Pachowski. It's absolutely a tour de force. Michał was able to solve this Helmholtz equation subject to these conditions here, not with one extra simplification, which I will only tell you if you ask me. And this is what he found. So he was able to solve this equation. And actually, you can already see what's going to happen without any calculation, because this is a Helmholtz equation. The solution of a Helmholtz equation are plane waves. And this will be a superposition of plane waves. So it'll be a superposition of plane waves e to the IPX with an exponential in the y direction. And this exponent in the y direction has to cancel the envelope. And so the dominant contribution will be where they precisely cancel, so there's nothing left over. So this will happen when P equals to square root of K squared minus delta 0 squared. So that's a new wave vector called Q, and that's precisely the periodicity. So the periodicity of these stripes, the periodicity of these stripes is set by the requirement that the solution of the Helmholtz equation cancels the envelope. And here you see, so this is numerics versus analytics. No fitting parameters, no nothing, and I think it agrees really quite neat. I mean, we have here the bifurcation point and this strange stripe which goes upwards. So this is really cool, and we can do a little bit better. So we can actually now try to make contact with experiments. What would experimentalists? They would do this tunneling spectroscopy experiment. In a tunneling spectroscopy, they would measure only the electron component of the density of states, at least for positive voltages. If they would do negative voltages, they would measure the whole component, so they can measure both separately. And this is what they would measure. They would measure in one component pretty much no oscillations, and in the other component, they would measure these pronounced striped oscillations with this wave vector Q. So I think this will be a pretty strong and conclusive experimental signature, actually, and something which I hope would be accessible for experimentalists. So it's 10 to 6, so we're going to leave 10 minutes for discussion. So I'm going to close with my concluding section. So this is a Majorana Landau level, friends. It's possible. It's possible to deconfine, to have the Majorana zero modes, which are bound to vortex cores, to liberate them from their vortex cores and form a Landau level. And what you need is Cooper pair momentum greater than pair potential over velocity. It's a deconfinement transition. A flat band appears, chiral symmetry protects it, their density oscillations are a very specific wavelength, a very specific wave vector, square root of K squared minus delta squared. In fact, you see here that K has to be bigger than delta over V, right? Otherwise, this wave vector will become imaginary. And the orientation of the stripes reveals the chirality of the Majorana fermions, which is another, I think, cool thing. And now this is just some fun thing, right? I have no idea. You know, once I say vortices, people say, let's braid them, right? I mean, there are even crazy ideas to pick up these vortices with an STM, move them around. Braiding of vortices moves you around in the degenerate manifold of the zero modes. So in this case, I'm pretty sure braiding of vortices would move you around in the degenerate manifold of the Landau level. So Landau level is massively degenerate. Landau level is massively degenerate. And you would be able to move around in this degenerate manifold by braiding the vortices. I have no idea whether it's useful, but it certainly sounds neat and something one might want to think about. Thank you very much, and I welcome any questions or discussions you might have.
Carlo, could you go back to the beautiful picture? Yeah, that's fine. That's fine. Now, there's a clear singularity that we're seeing where we see the bifurcation, but now when we look also in the places where the picture goes dark, exactly, it looks like if I could see in there, there would also be a singularity there.
Yeah, I think this is an interference. This is very much dependent on the type of vortex lattice which you choose. It's some sort of interference between vortices here and vortices here. And also, I'm pretty certain. You see, it's a massively degenerate Landau level. So one of the problems we had in comparing theory and analytics is to find which state in this manifold you would want to compare. And so what an experimentalist would find, I'm pretty sure what they would find is that this point here would very much depend on the wave vector. I mean, they would be in this degenerate manifold at a particular wave vector, and this particular wave vector most likely would tell them what you'll probably be able to move around this thing. I don't think this is very fundamental. It's interference of modes in this degenerate manifold. That's what gives it to you.
Well, but also it seemed like it was only present in the, I'm trying to remember now, in the numerical solution rather than the analytic solution.
No, that's absolutely true. And this strengthens the point, because in the analytics, this is just one, or it's a vortex pair. This is one vortex pair, and this is a vortex lattice. So this is just one single.
Okay.
One vortex pair, and this is a vortex lattice.
Okay.
Now, since you asked, now actually this. So I said Micha was able to solve this, which is a tour de force, but he had to make one simplification. The simplification is this: he can only solve it if the vortices. If you have two vortices on top of each other. So if you have an H over E vortex rather than an H over 2E vortex. There is a technical problem with an H over 2E vortex, which for the numerics, it makes no difference at all. And also the striped phase looks very similar. But there is a technical problem with an H over 2E vortex, which we were not able to solve. If anyone can solve it, you're my hero, absolutely my hero. And I'm sure Micha will also bow deeply. But after a couple of months of trying, I said, we're going to give up. Sometimes you have to say that, right? Give up and move on. That's my task as cheerleader.
Do the vortices that you encounter in this system, do they all have if I can express it maybe imprecisely, a winding number of 1, that is a topological charge of unity?
Absolutely.
Are there any doubly charged vortices that are encountered?
The vortices, all the vortices in this simulation are H over 2E vortices. That's the first thing to notice. So the H over 2E vortices. Mm-hmm. And they all have the same vorticity. So they all, let's say, wind clockwise, if the phase winds clockwise. Now, the vorticity is set by the sign of the magnetic field. So whether a vortex winds clockwise or anti-clockwise is set by the sign of the magnetic field. If you invert the magnetic field, the vorticity will change. And you could actually play around and say, what would happen if I would have vortices of opposite vortices, like a vortex-anti-vortex pair, which is curious, actually. It's something we have not yet, we looked at it briefly, but what happens if you have a vortex-anti-vortex pair is curious. It's fun. It's something you might want to investigate further. Again, this is just one single study. We worked on it for a couple of months, put it on the archive, and I don't know if it'll fly, if other people will be interested or not, or if it's just some strange, weird stuff. But there's lots of things to investigate here, absolutely.
Hi, Carlo. I have speaking of things to investigate, actually I have a question. It seems that in the story, the chiral symmetry plays a central role. Now, of course, in topological insulators, chiral symmetry is only approximate and relatively hard to ensure. Yes. So, can you comment on what happens if one removes the chiral symmetry?
Yes, I have a figure. I have a figure which I did not. I have a figure which I did not show, and I have to show it. I want to show it to you. So just bear with me for just a moment. Bear with me for just a moment here. Because of course I didn't. I mean, this is just something which I glossed over, waiting for someone to ask me, and now you ask me. So now I'm going to share the screen. Share screen. Stop share. Share screen. Here. Okay. So this is what happens if you. So chiral symmetry in this system is only exact at mu zero, at the Fermi level. So if it's undoped. So you could just push the Fermi level up or down. What happens if you push the Fermi level up or down is you see breaking of chiral symmetry, because so the green Landau level is now split. You see that it splits? It splits into two, an electron-like, because electron-like components, if you apply a chemical potential, electron-like states will move upwards and hole-like states will move downwards. So it slips, it splits, but it's still kind of flat. And so actually what we found numerically is that these Landau levels, they will remain flat all the way until let's say this one here, so this will move down, this one will move up. Once they intersect, it becomes a mess. So you can have Fermi energies up to the Landau level separation and nothing changes. That's why I'm pretty convinced that, this is not a strictly mu equals 0 calculation. Mu can be large up to the Landau level separation, and then once you cross the Landau level separation, then all these things hybridize and becomes just a mess. But non-zero mu gives you, and there's even some analytical evidence for this, because when we apply finite mu, we find that the first order, it doesn't mix chirality, so it preserves. It's just a diagonal. It appears diagonally in the Hamiltonian, just shifting one level up and shifting one level down.
Thanks.
Jay.
Yeah. Okay. Yeah. So so actually, yeah, Anton already asked one of my questions, which is not surprising, though. Maybe just to follow up. So when you say it's nearly flat, like just numerically, is it actually flat to the point that there is something more than first order perturbation theory that you're missing?
Okay. So first of all, for mu equals 0, Gall, who did all our numerics, was kind of concerned with this, and so he did a scaling analysis where he increased the lattice size, and because a finite lattice also breaks the chiral symmetry, so he did a scaling analysis, increasing the lattice size, and was able to convince himself that the splitting, that the level goes to. I should be a bit more precise. The reason why in the numerics chiral symmetry is broken is because in the numerics we have actually a finite thin film. So there's a top. I somehow glossed over that, but this topological insulator, of course, has a top surface and a bottom surface. It's a thin film, and all this topological protection only extends to the extent that the top surface doesn't talk to the bottom surface. So we include that in numerics. So we have a little overlap matrix elements between top surface and bottom surface, and they kill the topological protection. And in the numerics, what Gall checked is that as he makes this coupling between top and bottom surface smaller and smaller and smaller and smaller, the splitting goes to 0. So the chiral symmetry breaking at 0 chemical potential in a thin film topological insulator, which is the thickness of the film, that's one effect that goes to 0. And finite Fermi surface in our perturbation theory, we see that it appears in first order has no effect. We were not able to extend it to higher order, and numerically we just see that it doesn't do much. So
I see. Okay, good. But actually brought up another point. And you kind of mentioned it. So just in this response, what happens at the edge?
Yeah. So. Good question, and this is actually a follow-up one. And no, this is something we absolutely want to investigate. So what we did now is just to make this tractable numerically. Yes, we had a thin film, but it was spatially extended in all direction infinitely, so that we could work with the vortex lattice, and we could go to magnetic Brillouin zone. And so we had just the usual Bloch problem, so an infinite system. So we did not. Of course, the moment you say let's include edges. Oh my goodness, I didn't say that, I should have said this. All of this was done with Quant, and one of the prime developers of Quant is here, Professor Akhmerov. Thank you very much, Anton, for giving us this amazing tool. I can recommend it to all. And so it was all done in Quant, and this, the big simplification was that in the numerics, we had a translation invariant system in a magnetic Brillouin zone, and so we could go to really large systems. Now, the moment you say, let's attach leads, let's do transfer properties, let's have edges, obviously stuff which we want to investigate. I'm not giving away anything. Anyone would want to investigate that. But obviously, then immediately the system size you can do becomes way, way, way more smaller. And if you didn't tell me, please, Carlo, also add some disorder. before long, this is not something you can simulate very reliably.
So last question, and this is a follow-up on what you said to Bill. You said something about wave vector. So are those plots not the total density of states?
Yeah. So okay. So here, okay, yeah, absolutely. So the plot. Let me be very specific about this. The plot. We really tried to do the honest experimental thing, and so point contact probe. So it's an integration over the entire Brillouin zone.
Okay. So then there was no.
The plot which I showed you, which said share this plot here, right? This plot here is electron or whole component of the density of states, absolute value squared, summed over all wave vectors in the Brillouin zone.
Okay, and the color image, the pretty one?
No, the pretty one is just one particular K vector.
Ah, okay. Good, got it.
No, actually, I think Gal. I'm not quite sure whether we actually also made color. I think we also made color plots. I'm pretty sure we also made color plots integrating over the Brillouin zone, and it just
in the paper there are also the plots about integrating over the Brillouin zone. There's also a line that shows where this cross section is drawn.
It's all there in the. It becomes just a little bit more washed out, but not much more washed out.
I see. Okay. All right. Thanks.
Alan Migdal, is your hand up?
Yes. You mentioned that you weren't sure what applications or what this might be useful for. So as an experimentalist, I want to follow up. One thing we make significant use of are transition edge single photon sensors. So these are superconductors biased with current on their transition, and we look at when a photon comes in, it disrupts that, and we get a significant change in resistance. And it seems like this ought to allow for tailoring of that transition, either making it sharper or fatter, which might be of some use to improve single photon detection. Any thoughts on that?
Not really, but let me tell you the thought. I mean, okay, so when you say applications here, every single paper on this related topic mentions flat bands as the miracle for interacting systems. So you see, I have a flat band here. I have a flat band which is not atomic. So it's very easy to make an atomic flat band. You just bind electrons very close to some whatever, and then you have an atomic flat band. But that's not helpful. You want to have a flat band of extended states. If you have a flat band of extended states, it means you have quenched the kinetic energy. And so there should be all kinds of interesting many-body transitions once you add Coulomb repulsion. And this is supposedly the route to high-temperature superconductivity. So usually if you write a paper like this and you send it to Science, which we definitely did not do, no worries here, you end this saying that the final paragraph says, here we have engineered a flat band, let's add interactions. This might be a superconductor with a very high transition temperature. And I have no idea. I mean, this is, if you Google, I should mention it, if you Google Majorana Landau level, I Googled it. There's one other instance of a Majorana Landau level, and this is in spin liquids. So Kitaev spin liquids have Majorana fermions, and there a Majorana Landau level has been at least suggested. Now, spin liquid is, of course, a strongly interacting system. So there, I guess, it's fascinating what's happening here. Here, the good thing is that the interactions typically are not so strong, so we can try to understand more. But if you ask me, I think that if there are applications here, let's say interesting follow-up work, it would be to study what happens if these delocalized particles can now interact. And whether there will be some applications for infrared sensors, as you are suggesting, I'm not so sure. But
okay.